Hi everyone, what you're seeing is my homemade structural analysis X-ray machine, which I built over the last year. And before explaining everything, I'll show you a little montage of part of the video material that I've collected while building it.
Sous le soleil et sous la joie, et j'entends dans la musique les cris, les rires qui éclatent et rebondissent autour de moi. Entraîné par la foule qui s'élance et qui danse une folle farandole, nos deux mains restent soudées. Et parfois soulevés, nos deux corps enlacés s'envolent et retombent tous deux épanouis, enivrés et heureux.
The gentleman you're seeing is Mr. Max von Laue, the discoverer and inventor of the phenomena that I've recreated with my experiment. He was the discoverer of X-ray diffraction that led him to win the Nobel Prize in Physics in 1912. As you may already know, a big chunk of the material that surrounds us in the natural world are made of crystal structures, which means that they are composed of an organized arrangement of atoms that repeats throughout the space of the crystals. And the phenomena that von Laue discovered is that if you pass a collimated X-ray beam inside a particular type of crystal, it diffracts X-rays in a particular way that creates a diffraction image. The one that you're seeing on the right is the diffraction image, for example, of quartz, and the image on the left represents the experimental setup he used. The diffraction image is the fingerprint of the crystal, which represents the arrangement of the single atoms inside of it. So every crystal structure has its own diffraction image, and from the diffraction image you can work back to the single position of the single atoms inside of the crystal. This is the diffraction pattern of copper sulfate that he was able to get as the first diffraction image recorded in history. To do that we need an X-ray tube, a way to collimate our X-ray beam, and a system to control everything. Also, we will need a crystal and a way to record our diffracted beam. This is a structural analysis X-ray tube, which means that it is a particular type of X-ray tube that is made just for this job. Before this, let's see how a normal X-ray tube is made. This is a normal X-ray tube that you probably have interacted with without knowing, maybe at the dentist or at the hospital when they took you an X-ray. And it consists of a glass envelope surrounded by this lead foil, which prevents radiation from scattering around in other direction, aside from the one that we want, that is this little window here.
Inside we can find the anode, which is the part of the tube subject to a high voltage potential to accelerate the electrons.
That you can see there, which is the round part, and inside there is a button of tungsten. When electrons that are created here accelerate because of the high potential, they strike the anode and emit the X-rays at this direction, which comes out of the window here. As you can see, this tube is broken, and I also have the other part that goes into here. That part is the one which creates the electron. This is the filament, important part of the tube that is responsible for generating electrons that have to be accelerated by the high voltage potential and strike the anode. It consists of a simple filament like the tungsten wire bulb that you may still have in your house. It has two electrodes. Doesn't have any polarity because you can run this on DC or AC. So let's come back to this one. As you can see, this has some similarity to the one I showed you earlier, because it's made of glass and metal as the other one, but it has some really important difference which make it useful for our experiment, which is to get the Laue X-ray diffraction pattern.
In this case, the X-rays come out of these 4 windows down here at the base of the tube. They are made of beryllium, a metal that is has a really low atomic number. In fact, it is at the right of lithium on the periodic table, and this makes it a really great choice for letting through X-rays, because it doesn't absorb them, having this low absorption coefficient.
In the tube I showed you earlier, the anode was the part made of tungsten.
Instead, this time the anode consists entirely of copper. The copper is embedded in the metal that is painted with this white paint at the base. The difference is that instead of having a positive polarity high voltage on the anode and the filament at zero potential like before, here we have a negative potential on the filament and a zero potential on the anode. These two circuits are then equal.
I didn't tell you before, but the X-ray tube doesn't contain any air or gas, because otherwise it wouldn't work. To evacuate it, they used a vacuum pump connected to a glass tube that was connected here, and after evacuating the air, maybe using a turbomolecular pump or a diffusion pump, they simply used a flame to close the tube and to solder it shut. And then they put this little hat of silicone to protect it from damage. These 2 rings inside, they are the 2 contacts, like we saw earlier, that feeds the filament for the creation of electron. The filament, I don't know if you can see it, is inside there, surrounded by that metal focusing cap, which has the purpose of directing electron to the target. The target inside the base is made of copper. As you can see, it says 60 kV, which means 60 kilovolts is the maximum operating voltage. 2200 watts is the power that this tube can consume, which is really lots of power. And because it has this much power, you can see that there are 2 holes here and here, from which cold water is being circulated, come inside from one and come out from the other side. Water cools down the anode and prevents it from overheating and then melting, and then fusing the base of the tube, which then would implode and destroy itself. The other tube didn't have a system like this because it runs on less power, maybe 1000 watts, but only for 1 second, and doesn't produce all that energy that needs to be dissipated.
I spent a lot of time designing the electrical system, and it is one of the parts that changed the most during all of the different prototypes. It consists of the mains power that you can see I'm drawing now, that feeds a transformer which outputs a DC voltage between 10 and 30 volts. And this voltage is then fed to all the different parts that supply the different component. The component that I'm drawing right now is the main ZVS driver with his controller. These two together are the components responsible for controlling the power that is fed to the flyback transformer. Flyback transformer is what converts the low voltage direct current input of the ZVS driver to a high voltage alternating current output that is then needed for the next component, which will transform the alternating current to a higher level direct current, so higher potential output. And the next component is the Cockcroft-Walton voltage multiplier, that is an array of capacitor and diode put in a particular configuration so that they simply multiply the input voltage by a factor that is simply the number of stages. So in my case I have 4 stages, so if I input 10,000 volts, the output will be 40,000 volts. Obviously there will be some losses due to the inefficiency of the system and other factors. It has a negative polarity configuration that is shown in the drawing. To have a positive polarity you just need to invert the direction of the diode. In my case I need the negative because as I said earlier, the structural analysis X-ray tube needs a lower potential respect to ground to accelerate the electrons from the filament to the anode. Here I've also drawn the other important parts that are on the top side, the X-ray tube. Now I'm drawing the milliamp meter, which is needed to measure the current flowing through the tube, and that's a very important parameter, because by knowing the current flowing through the tube and the voltage of the high potential, you can simply multiply them and know the power that is being consumed, which is proportional to the X-ray intensity and number of photons. This is the final and updated schematic of all the components. You can see it contains another ZVS driver to control the low voltage of the filament of the X-ray tube. The voltage that is fed to the ZVS is controlled directly by the main power supply with a potentiometer. Another difference is this part right here, which is a 100 microampere meter in series, with a high voltage resistance that you can see here, that has a value of 1 gigaohm. So for every microampere that we read on the scale of the micrometer, we get a corresponding value of 1 kilovolt at the output of the high voltage side, so that we can know both the voltage of the cathode and the current flowing through the tube. The next task was to build all the high voltage component in this part of the schematic. For this part I started by soldering all the high voltage capacitor that you are seeing now, which are the blue circular things that are rated at 50 kV, and all the high voltage diode together in the configuration shown in the schematic before, and also the red cylinder you see is the high voltage resistor that is needed for the micrometer to read the voltage on the output. As an insulation I decided to use candle wax instead of oil, so I poured over the components inside a plexiglass box that I built, while trying to avoid giving fire to myself, and then I let it cool down until it became solid and could be transported. The other part that we need is this low voltage supply for the filament of the X-ray tube that is built with a ZVS driver, 2 coils of wire that transmit the power through the insulation, and a buck converter to regulate the power going through the filament. This is one of the first test prototypes that I've built. It consists of 2 coils of wire that are magnetically coupled, so it is possible to transmit power from the green-yellow cable situated in the outside of the high voltage circuit to the red cable, which powers the glowing filament that now is simulating the inside of the tube. And what you're seeing now is the final prototype that I'm using inside the machine. This is the small ZVS driver that I showed you earlier, with the same coil as before. It has a low number of turns on the primary side, and the secondary side that you can see here. Inside of this plastic bottle there is epoxy resin insulating the secondary side of the transformer. The insulation is needed because when this tube is energized, inside of the bottle there's like 60,000 volts, so you don't want a short circuit to happen, and so the power that is fed to the filament flows through these 2 cables from the secondary coil to the high voltage feed. The high voltage feed through is this plastic thing here that it's probably the 4th or 5th iteration. It is made of PLA plastic, which is a really good insulating material, so that the high voltage inside of the tube doesn't come outside and arc with the rest of the world and create a big mess. As you can see, to create a good seal I used some grease around the high voltage feed through to make a better connection between the glass and the plastic, so that the high voltage corona doesn't leak outside and ionizes the air. Finally, the power flows through the filament inside of the tube, where the high voltage accelerate the electrons, and the X-rays are produced on that little beryllium window. So now in this part of the video we can relax a little bit and take a look at all the building that went into this prototype. This is not the first prototype that I've built. In the intro of the video you saw also some of the other prototypes that came before this one. They were a little bit bigger. By the time that I got to this stage, I have learned how to optimize spaces, and so in this build everything is almost perfectly fit together with the other pieces to use less space as possible, so it is easier to bring around, and in my opinion it also looks way cooler than for example a tabletop of components all scattered around in a big mess of high voltage cable and stuff. That was the first ever prototype that I built. Anyways, that prototype I used positive high voltage multiplier, and in that case the voltage multiplier terminal was connected to the anode of the tube, that is the outside metal part, so it needed to be insulated from the rest of the world by being suspended on a big piece of plastic. Or I also used the book that you saw in the intro. But that was not the way the tube was intended to be used, so then I changed to what is now. The main reason for using positive polarity was that the filament could be grounded, and so it was easier to control the current flowing through it. At this stage of the build you can see that I've already put together the plywood and also I've connected all the voltmeter and the switches on the front panel that is made of transparent plexiglass. And now you see me painstakingly connecting all the terminals of the cable with their appropriate connector to the terminals of the switches and the meters on the panel. The black thing that you're seeing now is the radiator. The radiator that needs to dissipate the heat from the water that is circulating inside the tube. Under the radiator you can see a fan from Intel CPU that I've taken out. The fan needs to only move air through the radiator to have a better dissipation of the heat. I've also found a way to place the radiator with the other components inside of the box without it sticking outside. This last clip shows you the high voltage feed through that I told you about earlier, It's made of two parts. That is due to the fact that the geometry of the tube is not perfectly circular, so that the little thing you see me pointing in the video needs to accommodate the glass of the tube envelope that is sticking a bit inside of the circumference of the tube. So you simply mount it like that, and they fit together like a Lego piece. And then after this, the other piece that have the cables fit inside just by sliding inside it. The hole you see inside that piece are made so that the high voltage cable can be passed through. As you can see, it has almost a perfect fit, and PLA is a really good material for this because it also has a very good insulating properties, and it doesn't risk of coming out by itself, because with this kind of geometry all the pieces are stuck together really tightly. And I also used some grease on the outside to make an airtight seal to avoid ionized air messing around with my electronics. As you can see, they were so stuck together that I had to use some pliers to get them out. The two cables inside the tube are obviously the one that feed the filament. And this is how I connected the high voltage cable to the feed through.
So first of all, there is main power that comes from this cable and goes into this switch, and that switch controls the main switch power transformer that feeds power to all the different components. The voltmeter you can see here indicate voltage that is being supplied by the transformer, and as you can see, it can range from 0 to 30 volts. Now I will turn everything off, and this switch is only a reminiscence of the past prototype, but it doesn't serve any purpose, any real purpose. Beside this part of the controller, there is this switch which feeds this DC-DC buck converter, which then gives power when it's on to this LED. As you can see, I can regulate the power from around 5 to 20 volts. And when I turn this on, also the lamp turns on, and this feeds the filament of the X-ray. This part here instead is only for the high voltage. That also feeds the tube. And with this meter here, I can check the current flowing through the tube. And with this microamp meter, in reality it's a kilovolt DC that is being fed to the tube. Also, there is this mini buck converter up here, which can be regulated, and his purpose is to feed the part of this system that controls cooling of the components. For example, this fan here that you can see turns on, and also this pump for the circulating water, and another fan that is under this heatsink that you can see inside there, and is all controlled by this switch converter.
What you're seeing in this image is the collimator, and in my experience it is one of the most important parts to get the proper X-ray diffraction. So now I'll show you how I designed and how I made my latest model.
The job of the collimator is to take a cloud of X-rays that are shooting in all different directions, take only a portion of them and point that needle-like X-rays in one direction. It allows us to select a specific portion of space so that only X-rays coming from that part of the tube will be used. I have built two collimators in the past year while constructing the machine, starting with the worst type, that is also the first one that I built is this one. It simply consists of a LED disc that I fused myself with a pinhole in the middle through which X-rays should pass. it is bad, it doesn't work, and so I've upgraded to this big boy here, which is much heavier and works much better. It consists of a solid 1 cm thick LED block that I have fused and poured into a circular mold. The LED block is anchored to the other part of the support via these 4 screws, but the most important thing is not this, because this only prevents X-rays that are not coming from this hole from going into our sample. The most important thing is this copper tube right here. This copper tube is a 1 cm thick copper tube with a hole that I have drilled with a lot of pain, because I've broken some of my drill taps, and I've been able to then tap the 2 extremities so that I can screw on it this 2 part here, which if you haven't yet noticed, there is simply some nozzle used by 3D printer. As you can see, a 0.4 mm hole, the other one is a 1 mm hole, and so you probably can see, yes, you can see through it. These 2 in series create the Collimator system. I also chose to use a 3D print nozzle because they are widely available in different diameter that ranges from 0.2 to 1 mm, so I can do different experiment with different nozzle diameter. Let me assemble and let you see how it is mounted. You put this, the bigger collimator, which in this case is the 1 mm, inside. On the other side you put simply a washer here, so that the copper tube grips into it, and you can tighten the connection. And after that you simply screw this on like that, and it makes a really tight fit, cannot be distorted, and that is really important, because otherwise the beam would change direction with a little vibration or maybe by itself. And the second most important part of the collimator is the output nozzle collimator, which is the smaller diameter, because this is the one that creates final diameter that our X-ray beam will have, and it can be simply screwed on here like that. The hardest part was to make a hole that was straight through the tube, so it runs parallel to this surface that is parallel to the other surface here, and so it doesn't block the X-rays. If we had exit collimator extruder slightly offset the respect to the axis of the incoming X-rays by just a little bit over this distance that is around 6 centimeters, we would have completely blocked off the X-rays, and so the output of the collimator would be nothing. The collimator needs to be as long as possible, because I have experimentally determined that with a small collimator like this that has a path of only 1-2 centimeters, strange phenomena happens that I have yet to understand why. I will put some of the X-ray image that I got with this. Also, the length of the collimator is proportional to the dispersion of the X-ray beam output from the exit of the collimator.
So in simple terms, it means that if we have a large hole and a short collimator, like the first prototype that I've made, we get at a fixed distance a large cloud of X-rays, as you can see on the fluorescent screen on the right. But if we choose, like the last prototype that I've made, a smaller hole and a longer collimator, that is the length of the copper pipe, we have a much more focused point on the fluorescent screen that is smaller in size. So to get the same intensity that we would have got with the first beam, we need a much longer exposure time, and that is the reason for the 2 hours and more time that I've used to take some of the X-ray diffraction image. Another factor to consider is X-ray absorption by the crystal itself. In fact, the intensity decreases with the exponential of the distance. So even a crystal that may look thin for us may absorb a lot of X-rays. This is a simplified version of what is happening, because there's also other types of interaction between X-rays and matter, but that's too complicated and we don't have enough time to talk about that now. So the best way to reduce all of this problem is to select a good quality crystal and a very thin one, and that is one of the main things that I'm going to show you now.
So now we're going to choose our crystal for the X-ray diffraction. I've already taken some sodium chloride crystals, one of the biggest that were in the box of the episode, and we have to choose between them based on their characteristics. The most important thing in this X-ray diffraction to get a cool X-ray image pattern is the quality of the crystal, and for this we are looking for some big flat crystals, for example this one, and maybe some crystal that already have a flat face like this one. And also the most important thing should be that it's clear, because clear crystals are more likely to be made up of a single crystalline structure that will give very strong and coherent X-ray diffraction, compared to polycrystalline crystals that may look like a single crystal, but they are made of a lot of smaller crystals, lattice combined together. For example, look at this one. This is very clear respect to the other. Let me try to focus. This side is not clear, but it's because maybe it was cut. But in this side I can see through it. So this is a very good candidate for X-ray diffraction. And I also got on hand some other type of crystals, which are this menthol. You can see they are already very cool, very transparent. So to choose between one or the other, I based more on clarity.
While researching all of this stuff, I came across a method that we can use to grow crystals, and I also tried to experiment with it. It's called the vapor diffusion method, and it works if you have already the material that composes a crystal, but it is not a single crystal, so you want to transform it into a single crystal. And to do that we need the following thing: mainly a big jar like the one that you see here in the photo, and then we need a smaller jar that can fit inside of that. The next step is to fill the big jar that contains the smaller one with some solvent. This solvent must be soluble in the other solvent that we will put inside the small jar, but it should not dissolve the crystal itself. And for my experiment I tried to grow sodium chloride crystals, so I used the ethanol as the other solvent that you see here in red. Inside of the small jar I put a solution of distilled water and sodium chloride. So this method works simply by evaporating the solvent that is inside of the big jar, then diffuses into the solution of the smaller jar, and because the solution inside is saturated, they decrease the solubility of the crystal inside of the solution of water in my case, and so the sodium chloride start precipitating and forming hopefully single crystals. It needs a lot of time. The slowest the diffusion is, the better the crystal outcome will be. And for this reason you can put a lid on the smaller jar to make the diffusion of the ethanol even slower. And so after some time a small crystals start appearing at the base of the other container, and with more time we should be left with a bigger crystal. From this image you can see that I tried to recreate this method, and it worked out that bad. At the beginning you can see that the first crystal were not pretty good, but at the end I've got this pretty big and very very clear crystal on the top that unfortunately I lost, so I couldn't use for this experiment. In this next step we're going to reduce the thickness of the crystal to decrease the unwanted X-ray absorption. For this we need some ethanol and some distilled water that you can see on the right. So I fixed the crystal to a metal wire using some super glue, so that I can move it around and fix it in place. And to make our crystal thinner, I'm going to dip it inside the solution. This one is menthol, and menthol is soluble only in ethanol, not in water. So I'm going to dip the crystal inside of ethanol so that it dissolves for a little bit, and then take it out and dry with a napkin, so that I'm left with a thinner crystal that absorbs less X-ray, and so will need less time of exposure. I repeated the same process also with the sodium chloride crystal using distilled water, and after drying everything I was left with this very thin crystal that you can see in the photo. Now you're seeing how I mounted the crystal to be diffracted. It's simply glued to a piece of metal wire that is then attached with some tape to a 9-volt battery to keep it stable. Before performing our experiment we are going to get another substance that is crystalline, really thin and widely available. So now let's go and get mica. For this we are headed to the kitchen. I'm showing you a microwave oven transformer. You may ask yourself why. The reason is that we can find mica just inside of this. If you look very carefully, you can see that is what we are looking for. So now that I have a knife, I will try to make leverage. Maybe without breaking it definitely, so I can use the microwave. The mica was just covering this part of the microwave, which is the waveguide that has the purpose of guiding the microwaves that are produced in the magnetron at the right of this setup to the chamber with your food and heat it. So now that we've extracted mica, we needed to get a really thin single sheet. To do that I'm using a knife and trying to cut through the side of the mica, and as you can see I was able to peel off a little piece of mica that is really thin. So I proceeded to fix also the mica to a metal wire, and then we can proceed with the final experiment. What you're seeing here is the recording of the first time that I got a successful Laue image result. So you can see that some of the components are placed outside of the box because I was still testing them. For example, the radiator was outside of the box because I was trying out different types of pumps. To get our image we need to position the collimator in the correct spot, so that the maximum output of X-rays can be achieved. And to do that I simply put in front of the tube a fluorescent screen that I'll then lit up with the X-rays from a safe position, and saw the intensity of the dot on the fluorescent screen. As you can see right now, the beam is not very well collimating. That's because it misses the second extruder, and when I put that in place you can see that it is like a really thin dot on the fluorescent screen, and that's what we want. I then proceeded to place the crystal that we did before in front of the collimator, and as you can see from the speed of the video it took me a lot of time to get the right position so that the crystal was just in the perfect spot, and then I placed the photographic film that is sensitive to X-rays on a support that was just a bottle that I had laying around. I fixed it with some tape and placed the photographic film at around 1.5 centimeter distance to the output of the X-ray collimator and the crystal itself. Then I turned on the machine with the main switch, the buck converter for the filament and the voltmeter, and then the switch that powers the filament itself by the ZVS. After that is the time of the pump and the fan cooling all the components, and the amperometer that you see on the left to check the power consumed by the machine. Here I'm regulating the power and voltage fed to the filament and making a small test lighting on the X-rays to verify the voltage of the tube that you can see on the bottom right corner as the kilovolt meter reads. It indicates microamp, but in reality that is exactly equivalent to kilovolts. After some tests I increased the power to the maximum level, and then with the right switch on the bottom right corner I turned on the machine constantly and left room for the exposure. The big dot you see in the center is the part of the main beam that I fired at the crystal that was able to pass through it, while the other little dot in a specific pattern surrounding the main beam are the X-rays created by the atoms and so are less intense. From this image we should be able to determine the crystal structure you saw earlier, but that's very complicated math, so nowadays computer deal with that. By the way, the little dot you can see on the left is present in all the photographic film from the factory. After seeing this wonderful image that I find a little bit artistic in some way, I also have some other kind of image to show you. They are X-rays that I've taken of common object, and also of other living being that I will show. Before showing you the X-ray I took of my finger, I want to prevent those people who comment right away saying that I risk giving cancer to myself from doing that. And also we can talk a little bit about X-ray energy. There are mainly two ways in which X-rays can be produced. Continuous X-rays are the one that you can see on the right of this image, have large spectrum energy and are produced when an electron changes direction when hitting the target material. This spectrum shows you the energy distribution of X-rays when the high voltage applied. The hospital uses voltage that range between 75 and 130 kilovolts and are safe for short exposure because they are not easily absorbed by the tissue we are made of. This is a spectrum that I've taken off my X-ray machine with my homemade X-ray spectrometer when I operated the tube at high voltage and with the filament turned off. As you can see, the peak of the energy is at 40 kilo electron volt, which is the same as the one that you would get at the hospital. On the other hand, the characteristic X-rays are the one that I use to get a diffraction of Laue image. In our case, they are the copper characteristics line and have energy of around 8 kilo electron volt, which means that if I put my hand in the beam, all of them would be absorbed by my soft tissue. This is a spec I took off my tube while operating at low voltage and with the filament turned on. Oh, sorry, that's pretty messed up. This is better. So as you can see, the energy have a peak at around 10 kilo electron volt. The tube was probably operating at 30 kilovolt. The continuous spectrum, that is also called Bremsstrahlung, have a peak that is around at 1/3 of the tube operating voltage in energy. The reason we want low energy X-rays for diffraction is due to the fact that low energy photons have wavelengths that you can see on the right, and that wavelength is similar to the distance of the atomic structure, and so they can diffract and interact with the electron cloud. On the other hand, high energy X-rays have shorter wavelength, and so they are not good for X-ray diffraction as low energy, and that's why for the diffraction experiment I used 30,000 volt on the tube, and for taking an X-ray of myself I used around 100 kilovolt. As you can see, the first image didn't come out really great, so I then made another one, changing some parameters, and you can see that it's really better and sharper. The last subject that I also tried is this other volunteer, and it's really small, so it's really hard to see a lot of details. Unfortunately, our time is running out, but there's still plenty of phenomena related to X-rays and other kind of radiation that we can discover and experiment with. So if you want to see them, let me know in the comment, and also if you have any question regarding the apparatus that I couldn't cover fully on the more technical details because of time constraints, also you can ask there.